everyone. We are extremely excited to be here in Go Days conference. It's actually personally my first one ever I participate, and it looks so far so good. And I'm super excited also, we are super excited to be able to speak about topics we really care about and love, which is observability and programming in Go. We hope our talk will be very inspiring and actionable for you. So this is because at the end of this talk, we would like to, for you to know three things. First of all, why instrumentation and instrumenting backend Go application with actionable metrics is really essential. Second is how to add metrics quickly in Go, how to test them properly. And last but not the least, what are the common mistakes you should avoid? Mistakes that we've seen a lot during our work with metrics in Go, in the amazing but sometimes wild open source world. So yeah, before that, short introduction. My name is Bartłomiej Płotka. I am engineer working at Red Hat in the monitoring team. I love open source and solving problems using Go. I am part of the Prometheus team, and I also co-author of the Thanos project, a durable metric system that is meant to scale Prometheus. With me, we have also Kemal.
Hello, everyone. My name is Kemal. I am also working for Red Hat, and I'm working for OpenShift Observatorium team, and I'm contributing to Thanos as well.
Our job is mainly focused on building scalable observability solutions and platforms for OpenShift. But also as one of the major part of our job is maintaining Prometheus and Thanos projects on a daily basis. Those projects are focused on enabling monitoring via metrics for infrastructure server-side applications, for example, microservices running in Go. But let's leave that for now. Let's focus on very fun task. Let's talk about building load balancer, kind of. For demo purposes, let's imagine we want to implement application-level HTTP load balancer in Go. Why? Because why not? Yeah, it's fun. So let's imagine we have implemented transparent load balancer as presented in this diagram. From high-level perspective, we have couple components, Go components. First of all, we have a single HTTP server that implements serve HTTP method, so handler via awesome reverse proxy struct in standard HTTP util package. That reverse proxy allows us to inject custom transport, so round tripper interface, and we inject there our load balancing round tripper, which is called LB transport, which is internally using few components. First of all, discoverer, which allow us to discover to what targets we should proxy request to. Round-robin picker, which grabs those targets and picks the one in round-robin fair manner. So, replica 1, 2, 3, 1, 2, 3, which you can see below. And then at the end, round picker looks on, takes this target and forwards the request to the corresponding replica and get proxy the response back to the user. Now it looks great, like all should work, right? But is it production ready? That's the question. So let's say we deploy a couple of replicas of this service on production in front of some microservice, some replicas. As soon as it starts running, let's say I'm manually hitting the LB endpoint, and it works. Like it gives me the response I expect. So it works. We are good, right? We can go home. Well, not necessarily. It works for me, but are we sure it works for other users? Are we sure it works when I'm not checking, right? So, how many bad gateways error we actually have returning over time? We can't really tell. And what about discovery? Like maybe DNS was not working for a portion of time? How many replicas it discovers? How many it discovered yesterday at 5 p.m.? And what about round picking mechanism? Maybe, it's not really picking in round-robin manner. Is 1/3 of all requests really going to replica 2? What's the actual distribution? What's the distribution of the time? What if the user reports, for example, our load balancer being slow? Is it our replica being slow? Or maybe the load balancing logic is introducing some latency? And finally, how much memory we are actually using. Maybe we have a memory leak. what version we are running. There are so many questions that literally we need to answer, and we don't know what we need to answer beforehand when incident happens. That's why in SRE book, when you read that, you will find monitoring as the foundation of creating any reliable system before even implementing the system itself. As you might be familiar, some monitoring signal we can introduce, especially in Go, are traces, logs, and metrics. Guess which signal will give us an answer to those questions, like distribution of requests or tail latency? Yep, metrics. Metrics most likely give us the answer to our question. Answer that is, in comparison to logs and traces, maybe cheaper, definitely in real time, and definitely actionable. And, well, we can create an alert that will trigger another action based on behavior that just happened. Why Prometheus, though, right? Well, I might be biased, but Prometheus is currently the simplest and the cheapest option for collecting, storing, and querying metrics, as well as reliable alerting. It is part of the CNCF. It fits for the small application, but also for the bigger one, with help of CNCF projects like Thanos or Cortex. So let's figure out how to add a metric to our load balancer, how to answer this question. For example, what is the error rate for all the requests that just happened to load balancer? So we can do that by adding a certain metric, HTTP request total, count, and we essentially count those requests. Whenever a load balancing request occur, we increment that, reporting a method and the code that was responded to this request. We can introduce this metric really, really fast in a few simple steps. So let's see. First of all, we need to import Golang client, Prometheus client library. During our talk, by the way, we'll be talking mainly about this. And this is really neat library, actually Go module, which is designed to help with instrumenting any Go application. It's tiny, heavily optimized, and quite simple, and very popular. It's actually the official one. As a next step, we need to define variable. So let's do that. And let's name our counter, which is like HTTP request total. Let's put some description. Let's put some labels, code and method. Each unique value in those labels are essentially dimensions for our metric. Each unique value will actually create another series in Prometheus system. Next step is to actually count those requests. So let's create a simple wrapper over a serve HTTP, and which will increment the counter once the wrapped handler will respond with some code, and we need to have some trickery here to record the status and then increment our counter, right? Something that is easy to forget is also the next step, which is registering the metric in a registry, Prometheus registry. So let's focus what we are actually accomplishing by registering this metric. It's important for the next step, which is adding another handler for our servers. So we have LB endpoint, and we also need to have some endpoint for metrics. So and there is, like in Prometheus library, there is a Prometheus HTTP.handler for that. And usually it's a good pattern to put it in /metrics path. Now, okay, what we actually achieved, now is the question. How, from this, we can actually do queries and alerts. So, again, we defined and instrumented our metric. Now, under /metrics, we have our handler, which exposes a metric, a Prometheus kind of text, kind of metrics format, metric exposition, which looks like this, which is literally human readable. And as you can see, after many requests, we have some value of those counters. We literally have only two different responses, 500 and 200. Now, what is happening is that when you run a separate Prometheus binary, you point this Prometheus to your load balancer /metrics page, and it will periodically scrape, so collect those metrics every configured interval. For example, 50 seconds. And it will store those samples, and then when you visit Prometheus UI, you can actually query that data over time. So what you should see here is essentially an increase function over our counter, which means that we visualize here a number of requests per minute that we achieve in our server, which we have on our load balancer. So right now we have 120 per minute, and some of them were errors, most of them were successes. Cool, but this looks easy, right? Like all is fine. And in most cases it's fine. However, during this talk, we would like to present what we learn during a couple of years of developing and instrumenting Go code that is meant to be run on production in both closed and open source. And it's not, sometimes it's tricky. So together with Kemal, we'll go through a few less or more advanced issues we've seen and how to resolve them. And we are really passionate for you to be able to avoid them while you are instrumenting your application. Cool, first one, globals. So there was a saying in amazing Peter Borgon blog post, A Theory of Modern Go, magic is bad, global state is magic. This is very true, and also in case of Prometheus client, especially if you are instrumenting some Go package with some metrics, and then your project imports this package. But also, some open source users could import this package as well and use your library with some metrics. And also this library allows you to use globals for certain simplicity. However, somehow this usage leaked everywhere, and everyone just used those globals. So we want to break this. We want to make sure this is obsolete. And I will show you why this is a really bad pattern. So let's focus on, where is that magic and how to fix that. On example of our load balancer in Go. Okay. Let's take our example of HTTP request total metric. We have two global states here. First of all, we have a global variable, package level variable, where we store our counter. Second global state is hidden under Prometheus must register because it's using a global default register, which is like global library state. Now, okay, what's the issue here? Like, what's the problem? First problem is magic, right? Let's say I added my server request total variable, I registered that, and then some other, another package that we import, or even dependency of this package that we import, so dependency of our dependency, just register the metric with exactly the same name, it will panic. Like, our registration probably will panic. And the main problem here is that it will only mention where this second registration happened, and because you have stack trace. However, it will not mention where is the first registration. So you need to look, I don't know where, like it's so ambiguous, and we've seen those issues a lot when you're using global state, right? So yeah, please don't use globals. But there is a second issue as well, and it is lack of flexibility. So let's imagine we don't have like one endpoint, but we actually have three. 1, 2, 3. And so what happens if I instrument those endpoints like this? We have only two labels, code and method. So we are aggregating all requests, no matter what endpoint it was. So I don't have an answer on the question, okay, /3 endpoint. Like, what's the error rate for /3 endpoint? I don't know, because everything is together. So we are losing an insight, and there is no way for us to solve it when your library, whatever, is using globals. So let's fix it. And how we are fixing it? Well, by removing globals. Let's replace a global variable first. We create a struct, which you can instantiate, so you can have many of those, and the constructor creates this metric with a certain name and labels. Now, you can create such object and use it everywhere, which is easy, but still there is one global state that we didn't fix, so let's do it. Let's remove the default register it, and we can do it by injecting the custom registrar, and the constructor will register our metric. So we can create the registry then, create the new server metrics, and we are good. And are we good, right? Let's say I want to have 3 different metrics, 3 different HTTP request total metrics for different endpoints, right? And if I do this, this will panic as well, because again, we are registering exactly the same name, as you remember. But right now, in comparison to the version where everything was in global state, it is fixable, and we are in the control of our registry. We know what we are registering or not, because it's explicit. So I can go ahead and use an available wrapper, which is available in the Prometheus library, wrap with labels, and I can eject label to make it unique. So right now, it will register just fine. So I have /1, /2, /3, which at the end gives me amazing kind of grouping by endpoint. So I can finally answer my question, what was the error rate of the /3 for /3 endpoint? And yeah, it was 48 errors. 40 errors so far. So this is kind of how you should, in our opinion, build the instrument, the metrics. You should allow all the libraries all the structs that are using metrics. You should consider allowing injecting metric and injecting register, custom register, and never use magic inside your code. Okay, second pitfall, very important as well, as our title of the talk even, right? No tests. Okay, this is something I'm really passionate about. Metrics and other observability signals like tracing logs and profiles are rarely tested, right? Come on, who is asserting on your unit test what log message was actually produced, if the log was actually produced, right? And we don't do that because usually it's a human kind of information for humans. So we don't action on that in a computer doesn't action on that. So there's maybe no point. However, with metrics, in my opinion, it's totally different story, and I'm super serious here. The metrics have to be tested, and let me explain why. Okay, let's take our HTTP request example, right? Again, let's take some load balancing logic, and again, this is exactly the same as in diagram. We have and run tripper, which first asks for targets. It takes these targets and asks picker what target we should choose. And the chosen target, we essentially forward that to proper HTTP default transport, for example. And just at the end, we are marking what address was actually chosen in some header just for testing purposes, for example. And then in our server endpoint wrapper, the reverse proxy is invoked, and we record the status and increment our metric. So this is our logic of load balancer, let's say. Now, let's imagine we introduce a bug, we just were changing something, and there is a buggy recorder, which actually record always 200 code. So no matter if our load balancer or kind of backend behind the load balancer is returning you 502 or 404, it will always show the 200. And let's see what's the consequences of it. And well, first of all, let's see if the existing tests are catching this. So this is we are kind of we are testing our application, so we obviously have tests for load balancing, and let's go through this. First of all, we have some test cases. As you can see, we have certain targets that we mock, and then we mock the response from the backend. As you can see, we are triggering an error, and then we expect from the whole kind of backend thing from the load balancer to return code 502, which is bad gateway. And normally you have more cases, but let's focus on that one. Here in the test case, for each of those test cases, we again try to invoke the whole load balancer with a custom request. We record what it returns, and we make sure it returns what we expected. It's a table test. It's a really good pattern as well. I really recommend that. Now, okay, the question is, does it really catch our bug, right? Well, not. This is the bug, right? In this case, when we return 502, HTTP request total would be 200. So it means that your metric is suggesting that there was no error. This is very, very critical, because imagine that you have an alert on number of errors, or you are looking on beautiful graph and looking if there are any errors, right? And you see like all successes, although there were many, many errors properly handled, because the test succeeds and actually load balancing is working. However, our metric, our monitoring is not working properly, right? And there is no way to even know about that during your testing, CI process, whatever. So this is really, really bad. So let's fix this. Let's add tests for our metrics, right? So let's introduce another kind of package inside our Prometheus Go client library, and there is a clash with other test utils, so let's name it prom test utils. Let's add custom registry, obviously, our new metrics, which will be kind of mocked. And then before we do any request, any custom request to our testing request to our load balancer, let's assure that for now, there are no metrics incremented. And we do that by checking cardinality. So we are checking how many series will be exposed with this metric. There will be none. So this is what we expect. And we do that via, first method we want to introduce here, which is collect and count functions, sorry, not method. Cool. So let's now, this is huge. Let's now add an expectation to our case. We expect, metric with code 502 to be 1, to be incremented. Nothing else should be incremented. And let's assure that this is actually happening. So after everything, the test case was, and the load balancer was actually was performed the request, and we have the result. We check if with the toFloat 64, we extract the value of the metric for certain labels, so 502, which we expect, and we check if we have 1, right, in this case. And after everything, we also check if there is only one cardinality as well with the collect and count again, because we have only one series, and we expect only one series. So if you don't have this line, you could have many other kind of codes or like any other series incremented that we don't expect right now. So this is how you assert on them. So what is happening now is that, well, this test will fail because of our bug. So we finally caught our bug, and this is super, super important. And really, please do that. And maybe not for all the metrics, but just for important ones. And also, it is super useful to see when you are asserting on those metrics, how you are actually will be debugging your application furthermore if you have only metrics, right? So it shows you the behavior and the logic behind that, if it's even useful or not. So that's amazing, and we follow that on our projects like Thanos, for example. Awesome. Okay, so another pitfall, lack of consistency. What I mean by that? So there are useful methods for creating metrics. In SRE book, you would have the 4 golden signals, there is use method, ret method, and all those methods specify like from what aspect you should monitor your application using metrics. And there are like 2 advantages of this. First of all, it helps you to not forget about any aspect, right? But second thing is that you can use a common tooling like dashboards, alerts, and recording rules. There is even mixin project, which allows you to, if your application is following this method, you can actually use the same dashboard, for example. So let's focus on one method, ret. And ret means R stands for request per second. So what's the saturation of my load balancer, for example? E means like how many errors per second I have. D is what's the tail latency of my application. So this is like the 3 aspect that should be sufficient for like understanding your application. So let's focus on our load balancer. Does it satisfy ret method? So again, we have our server metrics. We have R, because this is the number of requests that we have. Fine. We have errors. Definitely we have errors because we have a code which can have 500, which can have success and errors both. So that's fine. What about D? Well, we don't have timing of the requests, right? So let's add that. That's pretty easy. We just need to add a histogram. And histogram allows us again, our serve HTTP wrapper to observe how long the process took, how long the request took, and then it puts the observation, not exact values of those, but like it puts the observation into certain buckets that you have here. So if it took 1 second or 2 seconds, it will be in the 1 second bucket, for example, because it's lower than 3. And and why we do buckets will be explained by Kemal in a second, but essentially with this we have latency, and our red method, well, we satisfy the red method and we can use the common tooling. So with this I will pass the mic to Kemal for further pitfalls.
All right, so we have yet another pitfall, and of course it's about naming, because naming things is hard. But like sticking to the naming convention should be easy enough, because we have official documentation in Prometheus. You should just need to follow those things. But this is one of the most common mistakes that we see in the community. As Bartek mentioned, by sticking to the convention, you would also enable projects like monitoring, mixing, those type of projects as well. So I would like to emphasize a couple of points from that documentation. First of all, you should have suffixes that describes your base units in your metrics. The base unit part is also important because you want to stick to your conventions between all those metrics that you have in your system. So the second one, you need to have underscore total suffix for all your metrics, for all your counters. This is actually going into the open metrics standard, so it will be mandatory. So please respect this one as well. And last but not least, underscore info suffix. So you need to put this for your metadata metrics. You can use this like version of your running service, metrics like that. So yes, yet another issue about the naming is the stability. So in here, I show you I'm declaring a metric, and it's the one that from the other slide, the previous slides, HTTP request total, where we track the number of the requests that we have in the system. And then we build an alert on it, as Bartek showed. And then for whatever reason, we decided to change the metric name because of some regulations or whatnot. So we put protocol in it. And now we have broken our alerts. So please try to avoid to do this, because this is one of the most common mistakes. If you stick to the conventions as well, you wouldn't break your graphs, your alerts, especially alerts, because alerts are kind of proactive, and you kind of depend on the alerts when you run your application on production. So yes, another popular topic is cardinality. When you talk about Prometheus and performance, it always comes down to cardinality. And what is cardinality? And the cardinality in this Prometheus context is the amount of time series that you expose. So especially considering the labels, you need to be careful about your labels, because each label value that you add to your metric, it kind of creates another time series, and you are incrementing your cardinality. So let's give an example. Let's say we already gave an example about HTTP request total. We have a label in there. We put HTTP method in it. And if we have just get and post methods, that means we have 2 time series. Cardinality is 2. But when we had another one, it will be 3. So let's see some bad examples, how we can introduce unbounded labels and increase the cardinality. So again, we have a metric, we register it. This is for the tracking the connection failures. So for this one, let's say we add an error reason, and whenever we have a connection error, let's just put that in there and increment our metric. What could go wrong, right? So when we scrape our metrics, this is what we get. You see a lot of gibberish in there, arbitrary error messages, and this is not what we want. Prometheus is like an aggregative metrics-based system, so this is not an event logger. So this would just like increase your cardinality, and it would easily break your system, and there's no value having this thing. So how we can fix this? So this was the stage that we were in. So let's introduce one of the tactics that we use in our systems. We use constants. So define some constant labels, and then create an helper method to map those errors to these constant labels. So like such an example would be like this. The important part is you get an error, you just return a constant label, and you put that in your labels so that you control everything in place. So yes, let's move on. One another pitfall about cardinality again. So histograms. So when you are dealing with the histograms, you need to be extra careful, especially about cardinality. Histograms are a bit more complex metric types compared to counters and gauges. But underneath, there are just one bunch of counters and labeled counters. So by default, if I remember correctly, it is like 10 or 12 counters. So, and they are very useful because they give you sampled observations. So you can, for example, usually you use that to track the request duration or the request size, whatnot. So since they expose, like, by default, 12 counters, we need to watch up the cardinality. Let's see an example. For sake of simplicity, I only define 6 buckets for this example, and we still use the HTTP request duration. And then we deploy our system, we check out our graphs. For a bit later, we realize that our average latency is too high, and we need more buckets to see what's going on and what could go wrong, right? Just add a couple of buckets. And that's what you get. And you, again, deploy your application, and you realize that you need more buckets. OK, YOLO, just add 3 more buckets. What could go wrong, right? And then you have them, that this looks nice, looks nothing could go wrong, right? Everything is fine. They keep increasing. And then a little bit later, you see that they keep growing and growing, growing. Because with the histograms, you have this multiplier, so each label that you add multiplies by 12 by default. So especially when you are using the histograms, watch out for your cardinality. And just don't increment your buckets like this. This is not the way. Yeah, adjusting buckets is an art form, more than science. So let's jump into that topic and see how we can actually see adjusting our buckets. So one of the other pitfalls is about poorly chosen histogram buckets. So histograms, they are using for observing request durations, request latency, or request sizes, as I told you before. But they are accumulative observations. So they have this concept of bucket because by this way, rather than aggregating all the raw data, you just collect them into the bucket, so they are cheap. Hence, they are cheap. By using these buckets, you need to watch out for your bucket layouts to watch out your performance or any other incidents that you could have. So let's see, again, a bad example. So we have 6 buckets, same metric. As you can see, those buckets. And you have an actual data of this. So since Prometheus using cumulative histograms, when you see O.1, it kind of includes the preceding buckets as well. So from this data, you could understand that we have really, really low latency requests, and they are all collected in the lower end of our layout. So how we can fix this? Again, client Go is our friend. It can help us here, and we use a function over there, linear buckets, and we just put in there. And by that, we have more or less better distribution. But the most important part is this in the slide is know your distribution. So when you like coming up with your layouts, you just need a way to distribute them correctly. And to do that, I kind of suggest that come up with your service level objectives and watch out what you want to watch out, and then lay out your buckets accordingly. So one of our last pitfall is not initializing metrics. This is one of the most common pitfall, and I want to show you how it goes. So again, we have this metric. This is the metric that we track the failed connections. And for this, we just define that, and we add 30 to that metric while running our application. OK, everything is fine. We have our metric here, but is it really fine? Like, when we check out the increase of that metric, we don't see anything. It's just 0. We don't catch it. Because like for the Prometheus, there is no way to, for Prometheus, there is no way to understand if a metric is initialized or subsequently scrapes just missed that metric. So to actually tell the Prometheus that everything is fine, you need to initialize your metrics so that it can catch all those changes. And most of the case, probably you depend, your alerts kind of depend rate or increase functions, so that's important. So how we can fix it? We can just, again, use a constant label and add that metric. And this with label values kind of initializes it. And then when we call that method, then we will see that peak increase. And then our alerts would work. Yes, to sum things up, I need to hurry a bit. I'm out of time. So yes, if you want to take 3 points from this presentation, please take those 3 points. First of all, monitoring is essential. Please monitor your apps, instrument them with like whatever you have, metrics, maybe traces, maybe logs, something, because you need to know what's going on in the running system. And then you can build alerts, graphs, any facilities that you could use in to understand, introspect your running system. And since you build those alerts and graphs, please test your instrumentation, because now you rely on them on your production system. And not last but the least, also kind of a low-hanging fruit, just don't use global registry. Avoid using global registry, as Bartek told. Magic is bad, so don't use it. So we have this demo. It's actually running, a running load balancer. You can actually run and see, observe. If you want to dig in more, just go ahead and check it out. And that's it from us. Thank you.